Hello, ladies and gentlemen. What we're going to do today is learn about the very basic model of an atom, talk about its anatomy, its parts, and how we interpret atoms and do what we call a particle inventory. We've been learning about the history of how the different parts and behavior of atoms have been discovered over the years, over many years, and it boils down to this. We discovered that we have a positive nucleus of an atom. It's a very compact, small region where two particles exist. We have our protons and our neutrons. And so what I'm going to do is kind of keep an inventory of our particles here, talk about each one as we go through. So we have our protons and our neutrons. Now, our protons. We discovered that the protons are positively charged particles, that they have a mass of this number, 1.67 times 10 to the negative 27 kilograms, which is a really ridiculous number. And we're not going to actually use that number. I'll explain why in a moment. But so these protons have this mass. We also discovered that the protons have a charge. We discovered the protons have a charge of what we call 1.6 times 10 to the negative 19th coulombs, which again, we're not actually going to use in this class. This is called a fundamental charge. Fundamental charge. This was actually discovered looking at electrons first, and then we discovered that protons match this charge value, but they're opposite in sign. Neutron. Another particle in the nucleus. It is in fact neutral. There is no net charge. That is because we discovered, and we don't have to really know this until much later in the year, we discovered that actually a neutron is a fused proton, or can be considered a fused proton and electron. Because when you have a plus and a minus together, plus 1 minus 1 makes 0, neutral. And we discovered that a neutron also has a mass of about 1.67 times 10 to the negative 27 kilograms. That means a neutron and a proton, they're not exactly the same size. I rounded here, there's a couple decimal spots beyond here which don't match, but they're pretty darn close in terms of mass. And so since a proton and a neutron both have roughly the same mass, the ratio of masses is 1 to 1. Because they're equal. And if the ratio of masses are 1 to 1, we said, okay, well then the mass of each object, to make things simple, because we don't want to work with this really small number, because that's really small. That's like a lot of decimal places. This number here, negative 27, realize this is 0.167, and then we got to go 27 decimal places to the small side. Actually, hold on, I messed up. This is 0.0000000. Now I have to go at least 27 spaces this way. So this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 6, 7. I mean, that's really small. That's like unimaginably small. That's the mass of a proton, and the mass of a neutron, and so since they're both really small, but they're both roughly the same, we're just going to say, you know what? They're a 1 to 1 ratio. A 1 to 1 ratio. Those masses, even though they're really small, they're about equal, so 1 to 1. That's the ratio, and that's called an atomic mass unit. Well, not quite, I'm lying a little bit, but for our purposes right now, it's very close to 1 atomic mass unit. Now, an electron, which we discovered were outside of the nucleus. They're floating around in what they call the electron cloud, and the spacing of the electrons are super far from the nucleus. In my picture, it doesn't really show that. The proportion is really not doing this any justice. If this were to scale, imagine going out to the football field and go to the 50-yard line, the middle of the 50-yard line, and put a dime. This is a dime, a coin. Put a dime in the middle of the 50-yard line, and an electron, which is maybe the size, well, a grain of sand or something like that. Take that little grain of sand, go out to the back of the end zone of either side of the football field, and put that little grain of sand down at the end of an end zone, and that's where you'd find the first electron in the electron cloud, comparatively. So that's a lot of empty space between the nucleus and the electron. And it's also showing you, in fact, and indeed, that electrons are much smaller than these central particles. Times 10 to the negative 31, that's a couple extra zeros to make this even smaller. As a matter of fact, an electron is about 1,800 times smaller than either of these two items. And because of that, because they're so much smaller, they say, well, we have a mass of 0. Which isn't really true. I mean, the electrons have a mass, they are particles, they are there, but the mass is so small, it's insignificant when I compare that to the mass of the other particles. It would be like going to the bathroom scale, reading your weight, and then somebody handing you a feather. If somebody hands you a feather while you're on the bathroom scale, is it going to change the number on the bathroom scale? Probably not. But is it technically extra material that you're carrying? Yes. And so that's the way we consider electrons. Now, so we're going to use these numbers, these comparative numbers. And again, they're very close to what we call atomic mass units. Again, I'm oversimplifying things for the sake of argument, and that's fine. We'll discover that later down the line if you get really into chemistry and technically into chemistry, I'm lying a little bit, and you'll say, Mr. Tapper's a liar. Sorry, not sorry. Well, let's get back to charge. We know that protons, again, are considered what we call a +1 charge. Why +1? Well, because electrons are a -1 charge. Well, why -1? Well, it was discovered that electrons had this what we call fundamental charge. Thomson helped go and discover that, and then Millikan finished the job. 1.67 times 10 to the negative 19th coulombs is the technical definition of charge, a fundamental charge. But again, what happens here is that the electrons have this value of charge, but negative. Protons have this value of charge, but positive. And since, again, these particles are equal in charge value, just opposite in signs, because they're equal in charge value, we can say it's a 1-to-1 ratio, except one's plus, one's minus. Okay, there's our charges. So we're not going to worry about these complicated numbers. We're going to worry about the simplified ratio version. Now, since a neutron is essentially a fused proton and electron, and you can do that because if you take a proton and an electron, because the electron has almost no mass, and you just add it to the proton, but the charges are going to cancel. So you get a charge of 0, neutron. Now, when I understand this, I can build an atom. And so we're going to talk about how we read chemical names or element names and talk about what we call mass numbers and do particle inventory. We're going to take a small break, and we'll get to that.